Okay, thank you, Dan. Great. Let me thank Chad for inviting me here. I think he's very brave because I'm a mechanical engineer. I was a little bit nervous, but after I hear Alan's talk, I think that's easy because a mechanical engineer, he's talking about robots, right? So I could be a chemist too. And today, I want to talk something, actually I do heat transfer, but I want to talk something that's not heat. It's light and water. And I will say something very unconventional. I want it to be challenged. So I also expect a lot of questions. I don't expect you to believe me, okay? But I want to convince you. There's something extraordinary that goes on when we say light and when we say water. So I originally thought about say even broader, but I found that I don't have time. So I'll just talk about this, what I call photomolecular evaporation. And I'll explain what I mean by photomolecular evaporation. And this is, as I said, it's very hard to believe. So we actually have a very hard time to publish. And I have, a very brave postdoc, spent 5 years, didn't publish a paper until I got a backdoor. So this paper just came out 2 days ago, so I didn't time it clearly. But we also have a paper just put on archive, and if you want to review what I talked, you can go to YouTube. I've been talking about this, trying to convince people. And so let me go to the remote click.
No, it should be this one.
Oh, this is my own clicker. Oh, okay. That's fine. Don't worry. This one, okay. Because so light and water, what's new? We know that water does not absorb visible light. And here is the solar spectrum. This is the green light, right? And the water can propagate 40 meters. And of course, we are happy when we see clear water, and that's just a sign that water does not absorb visible light, right? So this is a fact we all know. Let's go to the next fact. Well, this is actually a little bit controversial. It's actually an 80-year controversy. And it turns out cloud experiment measurement show there are more absorption than water calculation based on the optical constants of water. So those experiments, there are satellite data, there are people doing flights on top of the cloud, below the cloud doing the measurement. There are also ocean data. And those data just suggest there are more absorption. But the calculation say that's impossible. So this is a controversy, and because of those measurements is not easy, right? When you fly airplane above and below clouds. So it's understandable. And this is important because if you think about the entire Earth's climate, right? In the equator, it absorbs more heat, and the air rise, and then the north and south pole is colder. They see there, and then so the entire air movement is because of this. And let me go to the next fact. That is, of course, evaporation is a daily phenomenon, and we see this. And this morning, I took a picture from your beautiful seashore, and every time I see the sunset or sunrise, see the color, right? I think about whether there's a secret there. And I want you to see whether that happens. I hope I'll convince you. Of course, you know this is really scattered, right? So that's all we know. But I think there's one more thing behind we don't know. And let me give you another fact. When we evaporate water, right, we know the latent heat, we know the specific heat, and then we know how much energy it takes to evaporate water. Actually, going back here, this is the fact, right? Those are the facts of how much energy we need to evaporate water, and you can use latent heat. And now I'm going to evaporate water under sunlight, right? And I know how much solar energy comes in, and you can calculate what's the maximum of water you can evaporate. Because we know this is a thermal evaporation. You have so if I absorb all the sunlight, then how much water I can evaporate. And in fact, in 2014, we published a very simple paper. We just put something black on water surface, and capillary force will drive water to the surface, and the black material absorbs all the sunlight. And we say that's the maximum limit. We're getting very close to the maximum limit, and we didn't go beyond the limit. But then this was picked up by a lot of groups, and people started putting different materials on water surface and do the same experiment because it has a clear application in desalination and many other areas. So one experiment caught me by surprise. And this was an experiment from UT Austin Professor Guihua Yu's group, and they put black hydrogel, polyvinyl alcohol as the material, and they put some black absorber, in this case is polypyrrole, nanoparticles. And they say that, you see here is their measured evaporation rate. The evaporation rate is about 3. And the thermodynamic limit of thermal evaporation is about 1.5. And when I say this is 2018, I say that's impossible. So I just brushed aside. Guihua actually invited me to give a talk at the UT Austin at the time. I was the department head, so busy. I didn't know. I went there, I gave the talk, and I didn't know it was his work. And I was talk. I said, I don't understand why so many people work on it, because it's simple. But in 2019, let's see. Okay. Now I got. Okay. 2019, I had because I was starting getting interested in hydrogel on thermal properties. So I had a visiting postdoc, Yao Dong too, and he came over and he said he wanted to work on this evaporation, solar evaporation. We had worked there before. And I said, okay, I know this work, although I don't believe it, but maybe we should try it, right? And I also had a chemist visiting student, and she was, I'm not a chemist, so she was doing synthesis. So I say, okay, now we have a team. Why don't we make it and try to repeat it? In fact, we had trouble to repeat it, and we worked a half a year, couldn't repeat it. But I picked up the phone and I called Guihua. I said, can I send my guys to you? And he was very generous. And so I sent 3 people to his lab. They spent a week there, and they came back. They still couldn't make the material. I was just, as an advisor, said, what did you guys do there for a week? But anyway, luckily they brought a piece back, and we put it on our solar simulator, and it seemed to working. So we spent a few more months, and we eventually could make the material. And I actually had a chance, later on I was sort of get to the lab. This was actually 2021. I got time, I got in the lab, and I tried to make the material. And I learned it was not easy to make. So those were not the working material. This is the material I made in the lab as a graduate student. But those were material works. So once we found material work, we say, okay, what's happening? What's the mechanism? So I say, rather than putting the solar simulator, let's do the LED, because I work on optics, I work on heat. So is there any photon effect there? So I put a different light, different wavelength light. And this is what we saw. And first, if you measure the absorption, it's flat, no wavelength dependence. But then you measure evaporation rate. It peaks at around 520, right? This is a discrete LED. It's not a continuous wave. We don't know exactly the peak, but it peaks around grid. I was puzzling, right? And so I was very happy. We discovered photon effect. What photon effect, we didn't know. But there's one puzzle, so wavelength dependence. And this was another puzzle. When we measure the temperature above water and we turn on, so here is the IR imaging, and the blue is when we turn off the lamp, and the red is when we turn on the lamp. You put in energy, it's colder. And you also see a region of flat temperature, right? And this, you don't see this if you heat up water. It just continues decreasing. So, very exciting, but no physics, no what are the possible photon effect, right? And first, say we're hot electrons. We don't think that's possible because, in fact, Guihua, they have done a lot of work. They put the PPY, polypyrrole, carbon black, and titanium dioxide, and they, it works magic. Whatever material they put there, it worked. So we're not convinced there could be any hot, say, electron effect. Anything special with PVA molecules? This is also unlikely because the molecule doesn't absorb, right? PVA is a clear, doesn't absorb. So we're stuck. This was actually 2019. I said we had trouble to publish, right? Because we don't have an explanation. And Guihua, they had an explanation. They said, oh, water inside hydrogel is very different. Their water molecules are bonded polymers. Their water molecule weight, so this is the bond molecule, bulk molecule, and the intermediate. They say intermediate water molecules may have really low latent heat. But that's require a factor of 2 lower latent heat. And in fact, their experiment, they're even a factor of 3. I had to say I was not convinced. And then they had another experiment, sort of convinced me. They put a black carbon and they put a clear hydrogel on top. And they still have this, what I call super thermal evaporation. I said, that must be a thermal effect because hydrogel doesn't absorb, right? So in this case, sunlight coming in and heat up the black carbon, and the black carbon heat up the hydrogel. So it must be, he might be right. So then we say, okay, in that case, let me check. I do electrical heating. I don't need to do light heating, right? So we then went to the lab and trying to do the electrical heating. And this is putting heaters as close as possible to surface. So Yao-Dong worked very hard. I say, okay, make it uniform because we want the solar uniform heating and make it as close as possible to surface. So those are the different positions. And we're getting higher and higher efficiency, but we never get beyond the thermodynamic limit. So we're stuck. In fact, this was COVID 2021, another thing happened, and 1.5 years, no progress. But then I got a lot of time to read. Faculty members, we don't have much time, but I found a lot of time to read. And to my surprise, many groups have reported results super thermal evaporation. I thought it happens only to polymetal alcohol, PVA, but then I found first people put the different absorbers, and then people work on different polymers, and then there's some people say burn the organic materials, carbonized material. They're carbonized fruit, carbonized trees, they're carbonized cow manures. People just do very innovative materials, and they are reporting super thermal. And this was actually just from Guihua Yu's group. They've been sticking to polymetal alcohol, but they put different absorbers. So this forced me to rethink, okay, our experiment, the thermal didn't work. Originally, I saw the photon. So what could be a photon effect? What's common among all the materials, right? And it turns out, think about it, the only thing common among all the materials is they're porous materials. And porous material has a lot of surfaces, right? So could there be any surface effect that lead to this? And I know one. That was a photoelectric effect, right? And Einstein explained, actually I didn't know it was Hertz. Hertz did the experiment, and Einstein gave the explanation when photons come to the metal surface and they can knock out the electrons. So the question I asked, is there anything similar? Can photon come into water surface and lock out water molecules, right? Of course, there are problems. Water is not metal, and water doesn't absorb. And the photon energy, green photon is 2.5 eV, and hydrogen bond is 10 times weaker, right? You got a lot of excess energy if you just think of one bond. And then by this time, I did a lot of reading, and I also realized it's good that we have a lot of chemists, and people say water is the most complicated liquid, right? I got a question in the morning, how do you know whether water is clean? And in fact, I remember talking to another spectroscopist, and she said, I don't work on water, it's too dirty, right? So, but we know water is a hydrogen bond, a complicated hydrogen network, and in fact, chemists, you guys, arguing, some of you, how big of this water hydrogen network, say hydrogen network. And the numbers I read was like from 4 to 300. So that's the complication of water, which I don't claim I understand. But I need a physical mechanism to drive. So this is where it occurred to me that first, water-air interface, there are a lot of molecular dynamics studies say it's about 0.5 nanometer, right? And then when we have a light coming in at an angle, and Maxwell equation says that it's displacement component that's continuous across the interface. And dielectric constant of water at the visible light is about 2, air is 1. So across the interface, there's a factor of 2 change in the electric field. Now think about it. Over 5 angstrom, there's a factor of 2 change in electric field. And think about the size of a water molecule is about 0.5 angstrom. So the hydrogen atoms, the oxygen atoms experience different magnitude of force. And there seems to be a force imbalance. And with that, I say, okay, maybe this could be a mechanism to drive that happen. It's still very hand-waving, right? There's no theory. I have no calculation. I don't know how to calculate yet. But this gave us a picture, say, motivate us to do the experiment. And the first experiment say, well, I thought hydrogel doesn't absorb, but maybe it actually absorbs. And so I asked my postdoc, I said, why don't you dry the hydrogel and just add a little bit of water so that there's still a lot of interface? Then we go to measure absorption. And this is the experimental result. So let me walk you through. When measure absorption, of course, we have to measure because the material is very scattered, we have to use an integral sphere measure reflection and transmission and do subtraction. So the measurement is not going to be absolutely accurate. And here's water, few percent, essentially should be 0, so that's with the experimental error. And polyvinyl alcohol powder is 0. And the as-made hydrogel is 0. It's clear, it's 0, right? So once we start to freeze, we see the absorption. Freeze salt, we started already see absorption. That was surprising to me at the beginning. This was the experiment I was asking my postdoc to do. I said that you dry it, so the dry doesn't absorb. You put a little water and start absorbing. Right? The material itself, water and hydrogel doesn't absorb. But when you have a lot of interface, start absorb. And you put too much water, the absorption decreases. So we were on the right track. At least this is what we hypothesis. And then we went to measure evaporation. This is a hydrogel polyvinyl alcohol without any absorber. And you can say, so when the water covers the surface, you don't have a very high evaporation rate. But once the water recesses beneath, there are a lot of interface, you got a high evaporation rate. And then if you normalize this to the absorptance we measure, you got super thermal evaporation even for pure hydrogel without any absorber. And this is another experiment that this was Gui Hua's original experiment that got us to think he was right. We put a clear polyvinyl alcohol on carbon black. And now we shine that light from bottom. From bottom, then it heat up carbon black because no hydrogel there. And that we don't see any super thermal. But when we shine the light from the top, we see the super thermal evaporation. So those are consistent. And then even for pure hydrogel, it peaks at green. That peaks at green. We still do not know why it peaks at green. Green is the region when water is least absorbing. It's just mind-boggling to us, right? And now on pure hydrogel surface, we measure the air side temperature rise. We still see that flat region. If you heat up water, that's what you see. If you turn on the light, you see a flat region. And here is our explanation why this is happening. Light comes in, cleave out of water cluster, and water cluster break up in air, they cool down the air, and now the air becomes saturated, so there's a dynamic breaking and recondensation. So that's why in this region, we see a flat temperature region. Right? That's our explanation. And then we went to measure spectrum. And this is really just putting UVs near IR, and then we happen to be really cutting close to the near IR range for water spectrum. And then we see when we measure different height, when we turn on the light, measure different height, We see the peak shift. Some is a blue shift, some green shift. We don't really understand because this is a very messy system, right? It's in air. It's at the environmental conditions. So this gives us now some confidence that there's this process going on. And in fact, with that, we can also understand why making the material is not straightforward. Because what's happening is when this is a porous material, you got a cluster, and they could recondense. It's just like recondense, just like a recombination, right? Generate heat. But if they can come out of the pores, then you have the effect. So that's why making the material took some time. In fact, after the Yao Dong left, I still have another new graduate. He's still learning to make the material. But porous material is very complex, so we got ambitious. Can we look at this at a single water interface? Can we see the phenomena single interface, right? So we start looking, and in this case, and we were using LED. I got my former student to say, why don't you try to repeat it? He couldn't repeat it. In fact, we found some error even in our first single air-water interface experiment. And then we turn into laser. We say, let's use laser. And laser has an advantage. We can change the polarization, right? So our picture is that you need to have an electric field perpendicular to interface, right? So if the electric field is parallel to surface, that's called the TE, transverse electric field. So we need to have a TM, say, polarization that works. We also need to have light have an angle at a single interface. That's the expectation. So does that happen? The first one is heating. This is a green laser, 532. Water doesn't absorb. We should not see any heating effect, right? In fact, we should not see anything. And we see the temperature rise. First, this is a water temperature rise. And if the light is coming normal, there's no rise. And the TM you see here, it rises to the peak. And in fact, here are the two different ways, because we use the IR camera, and the other is actually putting a thermocouple in and out, because you can't put it into just under light, because that thermocouple will be heated up. But consistently, we see the peak at 45 degrees, and we see the strongest effect for the TM-polarized light. This is water. Let's turn to air. So for air side, what we do is, this is the so-called mirage effect. You have a laser coming in, the green laser, and then we have another small pump laser to measure the bending, because the refractive index will change when you have water molecules into the air. And you can see when we change the green laser intensity and also the different distance, we measure the bending refractive index change, and they respond to TM, and it has no response to TE polarization. So this is a green laser, because we have relatively powerful green laser. We don't have other wavelengths, so we need to measure other wavelengths. And in this case, we just use a pen laser, just a semiconductor laser. You can buy the $100, and different wavelengths. And we measure transmission. And when you change the intensity of the incoming, you excite water molecule, say water cluster near the surface. And then when you change the intensity, they will bend. So it's a self-pump and probe experiment that we're doing. And you can say this is a green pen laser, and it peaks at 45 degrees again. It's only for the TM polarization. And now when we do different wavelengths laser, it peaks at green again, right? It peaks at green for the TM light. And this was the hydrogel evaporation experiment. that pixide green. They all come together. And now I use back to the green laser, 45 degree, but now I actually heat up water, so there's a rising plume. If I don't heat up water, it's too heavy, you don't have that rising plume. So if I heat up water, I turn on the laser, you see this is TM laser on, and it has a sharper temperature decrease near the surface, and then it has a flat temperature region. And you don't see that when you have a TE polarization. So this also checked out, and just to remind you, we saw this on hydrogel surface 2019, and we measured this the last 2 years, right? So this is a different experiment, but a consistent phenomenon. And then we went to do UV-Vis again. And this is a UV-Vis experiment, and this is heated up without laser, and you measure the absorption. And with laser on, you got a lot more peaks. And compared to pure single water molecule vapor reference, this is a lot more new peaks. We still don't know, we can't tell. Maybe this is where machine learning will tell us what are the cluster size, and we don't have very good information. But this is another one. This is Raman. This is a lot more clear. And in the Raman experiment, what we need to do is this is a confocal Raman, so we pull the focal point above the water surface so that you can get signal from the vapor phase. And also the beam is divergent when it hits the water surface, and that will generate photomolecular, what we call photomolecular effect. And here, the red is the focal point on water surface. You measure water, and then when you are off, this is a single water molecule peak. And you see a lot more peaks, right? Very clear. And this is a reference that people do water cluster. This is a 46 say cluster, and that's say the infrared spectral absorption data. But it just it's not a one-to-one comparison, just to show that we are seeing the clusters. So how large is the absorptance? We still have trouble because it's not a, say, large number. And here is just an estimation based on the energy balance. And basically, we do lateral evaporation without the light so that we could extract based on the surface temperature measurement, air temperature, surface temperature, latent heat, and then we can extract the heat transfer coefficient. Then we turn on the laser, we do the water temperature measurement again, and from that, we model what's the absorptance. And so for 520, actually this is 532, at 45 degree, the absorptance is 0.8%. That's a pretty big number, right? Really surprising. And then we also measure evaporation rate. In this case, we have to heat up, because if we don't heat up, we can't measure evaporation. It's just too close, it will recondense to the surface. But when we heat up a little bit, you can see this is a TM, and this go back to TE, and this is the original no laser. And the difference gives us about 0.07 at a single interface. So now I have the absorptance, I have the evaporation rate. I can estimate how many water molecule a single photon lock off. And that number is about 20. So a photon come in, lock about on average about 20 water molecule. That's what we infer. Let me come back to the originally the cloud absorption alarming. And in fact, I was sharing this with my wife. She's an accountant, right? And she said, oh, weatherman said when after the sun burned the fog, maybe there's something to do. So at the time, I didn't know cloud alarming. I said, we can do a cloud experiment. So we make a chamber, cloud chamber, right? This is just a clear chamber. We generate water droplet inside. And green light should a lot of heat up, right? And so we use different LED, and you can see here, it heats up and it peaks at green again. The green light actually get absorbed and can heat up clouds, right? In the past cloud study, people just actually assume there's no absorption. They actually use the green light transmittance plus reflectance equals 1 to cherry pick the data. So like I said at the beginning, I'm here to challenge conventional wisdom. I fully anticipate you should challenge me, and you don't need to believe me, but this is what we believe was happening. And we got over 20 different experiments that are consistent with anticipating what we hypothesized. But let me just raise those questions, because this is something that happens every day, right? And really, it's a phenomenon I think we don't know, and it should have a lot of implications. So we see this is a cloud, fog, ocean. Ocean has a lot of foam, soil surface, and plants, right? How does this impact the weather and global warming? Water is actually, stronger global warming agent than CO2, contributes twice more global warming than CO2. Why this effect picks at green? We have no idea. And does it happen to other liquids and even solid? And in fact, I remember I was talking to only person who sort of believed me was Eli Yabelovich. I was telling him, and he said, "Oh, you know, any material surface absorption is an intrinsic property. People just don't talk about it. People don't understand it." He gave me some number in solid surface, like 10 to the minus 4 in gallium arsenide, and 10 to the minus 7 in silicon, right? I said, well, I think it's probably similar mechanism because gallium arsenide is polar. And how we quantitative, we still have trouble to do quantitative, and how we model, including how we incorporate into Maxwell equations, right? But this is even, bring me to ask why the plants are green. Of course, biology says photosynthesis, and we know. But evolutionarily, why plants choose to reject the most energetic spectrum of solar energy? If you look at the coral reef, they're not green. In water, they have not water. And in air, is it green because they avoid the evaporation? I don't know. I'm just raising a question, right? And so with that, let me stop here. I want to thank you for inviting me and for listening to me. And as I said, I fully expect there are a lot of challenges. You don't need to believe me, but this is what we see in our experiment. We may have problem in our experiment, so tell us. We actually had the mistakes we realized at the beginning when we had a light come into balance, and then we measure big effect. But then later on, we realized that light leak to the balance actually impact the balance reading. So we had to spend another 2 years to do another complete new sets of experiment. So thank you very much.